video, we shall be discussing sum of subset problem which also adopts the backtracking technique. So here the problem is to find a subset of a given set A which has n positive integers a1, a2 and so on till an, whose sum is equal to a given positive integer d. For example, if set A has elements 1, 2, 5, 6 and 8 and d is equal to 9, then there are two solutions. The first solution set may have elements 1, 2 and 6, adding which we get a sum which is equal to 9. And similarly, the other solution to the problem could be having a set with elements 1 and 8, the sum of which is again equal to 9. Thus, for same instance of a problem, we may have more than one solution, or for sometimes some instances of this problem may also have no solution. The state space tree can be constructed just as a binary tree for any given problem. The root of this tree represents the starting point with no decision about the given element made as yet. Its left and right children represent respectively the inclusion and exclusion of element A1 in a set being sought. Similarly, going to the left from a node of the first level corresponds to inclusion of the set element A2, while going to the right side of the tree of the node corresponds to exclusion of the element A2, and so on. Thus, a path from root node on the ith level of a tree indicates which of the first I numbers have been included in the subsets represented by that node. We record the values of A dash, the sum of these numbers in the node. If A dash is equal to D, we can either report this result and stop, or if all the solutions need to be found, we can continue by backtracking to the node's parent. If A dash is not equal to D, we can terminate the node as a non-promising node if either of the two following conditions hold. That is, if S, the sum plus the sum of S and the next element in the set, that is AI plus 1, if it is greater than D, or if sum S plus the all other elements in the set A is less than D. So if these two inequalities hold, then you can terminate the node saying that it is non-promising or it is not yielding a desired result. So let us consider a problem, or let us try to apply backtracking algorithm wherein set S has elements 3, 5, 6 and 7. Set S has elements 3, 5, 6 and 7, and the sum that we want to get is given by D, which is equal to 15. So for convenience, what we do is sort the sets elements in increasing order. So if you observe, already the set S has the values arranged in increasing order. So we begin with node 0, the first node. For the first time, we include the first element from the set, that is 3. So 0 added with 3 gives us a node whose value is 3. Then we try to include the second element in the set, that is 5. So 3 plus 5, sum yes, plus the next element in the set, that is 5, gives us the new node S dash whose element is 8. And then considering the next element in the set, that is 6. So with 6, 8 plus 6 gives us a new node S dash which is equal to 14. So now 14 plus the next element in the set would give us a result that is greater than 15. So therefore we consider that this node is a non-promising node. So hence we backtrack to its parent. So now I have already told that the left edges represent the inclusion of the elements, whereas the right edges represent the exclusion of the elements. So here towards the right of element, towards the right of a node which has 8 in it, we go with the exclusion of element 6. So 8 not added with 6 still remains 8. So now let us consider the last element in the set, that is 7. So with the 7, adding up 7 to 8, you get a solution which is equal to 15. So we get the result to be equal to D. So similarly, backtracking back to its parent, that is 8, and considering a situation wherein you do not consider the last element of the set, that is 7, then you get back to a node whose value is 8 and 8 is less than 15. So it satisfies the second condition here. So therefore we say that this node is also an non-promising node. So then from 8, if you want to find all possible solution, then from 8 we again backtrack to its parent. So its parent is 3. So left edge we had considered the element 5. On the right edge we shall try to eliminate the set element 5. So therefore the node now has only 3 in it. So after it, we shall now try to include the third element of the set, that is 6. So 3 plus 6 gives us a value 9. Right? And then if we consider the last element of the set, 9 plus 7 yields us a value greater than 15, which satisfies the first condition. So therefore we consider this also to be a non-promising node. And then again, in order to find out all possible solutions, we backtrack from 9 to node 3, and this time we move towards the right, wherein we do not try to include 6 into the solution set. So 3 without adding it to 6 remains 3 itself, and if we want to include the last element into the set, then 3 plus 7 gives us a value that is lesser than 15. So therefore it again satisfies the second inequality. So therefore this also tends to be an non-promising node. So after finishing all these nodes, we now backtrack from node 3 to the root of the tree whose node has a value 0 in it. So now towards the left we had first included the element 3. Now without including the element 3, we get a new node whose value is equal to 0. Then let us try to include the element 5 into our solution set. So if we include 5 in it, so the next intermediate resultant node here is 5. So the next time if we want to include 6 also into the solution set, then 5 plus 6 gives us 11. So if you also want to include 7 into the resultant solution set, then 11 plus 7 yields a value that is greater than 15. So therefore we also consider that this is a non-promising node. So therefore backtrack to its parent. So going back to node which has 5 in it, we shall now try to find out a solution set which does not have element 6 in it. So therefore 5 without adding to 6 is still equal to 5, and the next time you should try to include an element 7 in it. So 5 plus 7, 12 is less than 15, so therefore it again is a non-promising node. So then again backtracking from 5 to its parent, that is node 0. So towards the right of this subtree we have an edge wherein we do not try to include 5 into our resultant solution set. So therefore the node still remains 0. So 0 plus, if you try to include all other elements, then it is still lesser than 15. So therefore this also tends to be a non-promising node. So the solution to this problem is, see, the sum that we want to achieve should be equal to 15. So the solution set, let me say the resultant set R is now equal to, for the first time, we include 3. For the next time we include 5, and then without 6 into it we now include 7 into it. So the solution set now has 3 elements in it, that is 3 plus 5 which is 8, 8 plus 7 which is equal to 15. So this is how the state space tree of sum of subset problem looks like.